All right, everyone. Hello. My name is Ramon, and I am one of the participants in the InnoCyPES project. I am doing my Ph.D. in the Norwegian University of Science and Technology, around 4 months to finish, so let's see how it goes. And this presentation today, I will talk about the work that I have been doing in partnership with Siemens Gamesa. It's about estimation of short circuit currents from type 4 wind turbines. And although I am the one presenting, you can also see in this title slide the name of Gabriel, one of the presenters from yesterday. Although he is not in this presentation specifically, this study only exists because of him. So thanks a lot, Gabriel. And let's start. So this is the content for today. I will briefly talk about the importance of this SCC, abbreviation for short circuit currents. So the importance of SCC studies and overview of grid codes. I will recap a bit on, sorry? Okay, maybe the sound was not so good so far, sorry for that. Yeah. I will recap a bit on Newton-Raphson power flow methodologies because that's what I have used to do this research. I'll talk about the challenges in these kind of approaches to do fault analysis. And then let's see how time goes, but I will try to do a bit of a demonstration / tutorial and show a bit of current results. So at the bottom right, you see a link. If you are willing to do that, you can go to this link and download the MATLAB files that are in there. And it's up to you, of course, but if you want to do that, then you will be able to follow up during the demonstration as well. It's exactly the same codes that I am going to use. So when it comes to these studies about short circuit currents, in a very summarized way, because even if I wanted to talk about it in a detailed way, I'm not an expert. So very briefly, these kind of studies, they are helpful for protection studies, design and coordination. So we have softwares nowadays like ETAP and Aspen that already do this kind of estimation, but a lot yet has to be implemented when it comes to including these inverter-based resources. And also such studies, they support stability assessments. We have seen, for example, that in many cases that we are unable to estimate the current contribution from an IBR, such as a type 4 wind turbine. Sometimes it means that there is a problem with the stability, even in real time, not real time, a time domain simulation such as EMT simulation. So, and about the grid codes, also in a nutshell, a grid code is something that will dictate the behavior of an IBR so that the operation happens in a proper way. This is something that changes a lot from country to country, from TSO to TSO, but I will try to explain a bit the equations here. They are in a certain way representing a grid code in a generic way. So we see here, for example, in the first line of the equation, that there is a rule dictating how the positive sequence reactive injection should occur. You see that there might be a deadband for the voltage. The pre-fault current might be added or not. This depends on the grid code. The K factor, which is the proportional gain for the controller, it can have different values and so on. We might, in the second line, we see that we might not have reactive injection for a negative sequence, or we might have. And I don't think I need to go through every detail, but the essence here is that you can see that there are different ways for us to define the rules in the grid code. But regardless of what are these rules, the wind power plant should be grid compliant. And just one one detail which is interesting about active injection is that the IBR will try during a fault to inject the same active power that was generated before the fault. But sometimes this is not possible because there is a current limitation related to the capacity of the converter. And then it will just, as you can see in this very last equation, it will just inject whatever is left out of the capacity. There is a maximum capacity, and then there will be a reactive injection, as you see here. And then whatever is left, we inject as active current. So this is more or less how a grid code works. So changing a bit the topic in a certain way, just to very briefly remind you about these Newton-Raphson methodologies. The whole idea is that we want to find the value of the function through an iterative process. We take guesses for whatever variables we want to find, and then based on derivatives of equations, of mismatches that we want to minimize, we can step by step reach an equilibrium point. So this method, Newton-Raphson methods, have been used in power system for decades now. This is not new to anyone in electrical engineering, but this slide is summarizing the more standard approach that most people use. So in summary, we have equations that tell us the active and the reactive power. And what happens is that for different buses in a electrical system, we have specified active and reactive power. This means that it's a value that is known. And then we have the active and the reactive power, which have been calculated through these equations here on the left. And we want to minimize, not only minimize, we want to bring this mismatch to zero. If we bring this mismatch to zero, it means that we found the state of the system. And this is the whole idea about using a Newton-Raphson approach to estimate the state of the system. As I said, this is already very well known. So what is not so typical is the inclusion of current buses in such systems. But it's not, at the same time that it's not typical, it's actually quite simple, because we have equations as well that tell us about the currents, active and reactive currents. So if we have certain specified currents instead of power, active or reactive power, we can do exactly the same. We can just increase our Jacobian matrix in the Newton-Raphson methodology. We include the mismatches related to these current buses, and we just do the same that we were doing before. And by doing that, we are able to solve problems that include current buses. And why are we interested in current buses? Because IBRs, during faults, they will behave as a voltage-dependent current source. And this is pretty much what the grid code says. You see that the current injection depends on the voltage level. This Vres is the voltage level during fault at the terminals of the IBR. But there is one detail here, is that differently from the standard Newton-Raphson approaches where specified power is a known value, a number, which is constant and therefore the derivative is zero. Here, the specified currents are not constant. They are actually given by the equations of the grid code. And there is actually a mistake in this slide, if you think about it, because when I wrote here the Jacobian as the derivative of the calculated currents, because this C up here, these are calculated, this is incomplete, because if the specified current is not constant, it means that there will be derivatives associated to these specified quantities as well. And this is part of the challenge in addressing fault analysis with Newton-Raphson methodologies. But this is the overall idea. So, and talking about challenges, There are many others that we don't even have the time to discuss, but just to name a few, if you want to do fault analysis using Newton-Raphson methodologies, we should capture some aspects related to the real components. If we think about it, the PLL, for example, it works in the DQ frame, not in the ABC frame. It means that the standard way to calculate the currents will not work. We must make adjustments related to this conversion to the DQ frame. And especially as well, addressing unbalanced faults can be quite challenging. As you might know, one of the ways to address unbalanced faults is using symmetrical components, and doing this with Newton-Raphson it's not trivial at all, although we don't have time to go deep about it. And also including negative sequence injection, which basically means that we would be adding sources in the negative sequence component of the sequence components circuit, as you can see in the image down here. And yeah, now we are going to the tutorial / demonstration. I know that looking at the code that someone else has written it's quite bad, but I'll try my best to make a few things here clear. Of course, I will not go through the lines of the codes. There is no point in doing that. I just want to show you some very specific parts of it. So there is one code here, which is written using, let me get back to the slides, using exactly this methodology shown in this slide. So it is calculating the currents with the standard equations up here, and also calculating the derivatives based on these equations. And let me try to show you. Yeah, so these ones, this is for active and reactive currents. That's what we have right here. And let me just go to the derivatives. And this piece of code here is calculating the derivatives for the Jacobian. The equations themselves don't matter, so no worries about that. But it's doing it exactly like this. And if I run the code to estimate the currents, just to give a bit of context, here I have 3 cases with different voltage references, different SCRs, different fault locations. And the intention here is to properly estimate the behavior of the IBR. And here we have these lines right here. These are the results that came from an EMT model that has been field validated by Siemens Gamesa. So this is pretty much what we want to get. This is a validated result. So if I run this code, if we take a look here, so the small axis here, the blue, pink, and purple, these are the results from the EMT simulation for voltage, reactive current, and active current. And you see that the voltage is more or less okay, but the currents are not good at all. There is quite a mismatch, meaning that it's not really properly estimating the currents. And then the question is why? Why is this happening? Because I can assure you that over here, and also in the code, there is no mathematical mistake or anything like this. The equations are all correct, but still we have this mismatch. Don't know if anyone want to try to guess. I actually gave a hint about it a while ago. Maybe I'll put some pressure on Elisabeta's student who is here in person. Want to try to guess? Or want to skip? The hint is in this. Let me see if I know. Yeah, the hint is here. No, no, no worries, no pressure. It's when we have not seen it before, it's tricky to see it. But what happens here is that, as I said, the PLL, which is related to the control of the converter of the IBR, it happens in the DQ frame. It means that if we try to use standard current equations to do the calculations, it will not work. And not because the equations are incorrect, they are correct, but the DQ frame is something else. So if you think about it, when a current is calculated in the DQ frame, it can be given by this equation right here. So active power minus J, which is the imaginary uh, element, let's call it like this, times the reactive power divided by the voltage magnitude, only the magnitude. The phase doesn't matter. So in the DQ frame, it is like this because it is aligning the currents with the D and Q uh, frames. So if we work around these equations, we know that this is a standard power equation. We know that voltage times I forgot the name of this in English, conjugate, I think, of the current, but I think you get what I mean, is equal to active plus reactive power. So if we do some work on this, we reach these equations here in bold. So you can see that the active current in the DQ frame, it not only depends on the active, but also on the reactive currents calculated through the standard equations. Right here, these are the standard equations. And you see that in the DQ frame, both of them show up in both calculations for active and reactive currents. And also this delta K, which is the phase of the voltage of the IBR. So these are the current equations calculated in the DQ frame, and it will only work if you use these equations specifically. But this means also that not only you have to establish your mismatch in the power flow using these equations, you have to change the derivatives as well. Because as I said, a Newton-Raphson approach requires that you calculate the derivatives of your mismatch equations, and so we need to do that. So I have it in this slide uh, just to make things a bit faster. So I don't know if anyone has downloaded the codes and have them open in MATLAB, but let's see if we can do it here. Just I know this is a kind of boring in a certain way, but the idea is that you get a bit the feeling of how this is done. So here I am creating some vectors to store the values. So I will create an IADQ for the active current in the DQ frame and a IRDQ for the reactive current. So, and here in this piece of code, it's where I was calculating the currents. So here I will put my new equation. So you can see the active current in the DQ frame, it is the active current times the cosine of the voltage angle. So, and this here is the active current. So let me erase this. Plus the reactive current times the sign, but this is wrong. There should be the phase, cosine and sine of the phase of bus K. And for the reactive current in the DQ frame, this will be reactive current times cosine minus active current with times sine. This part of the code is a calculation that happens before the iterative process. The iterative process beginning this while right here in line 95. So down here somewhere, if I can find it, I have to put the calculation as well so that it will update in each iteration. I think everything should be correct. And then comes the part with the derivatives. Because here, as I said before, this from line 135 to 159, this is where I have the derivatives, but related to the standard current equations. So now I will adopt them based on the DQ frame equations. So we have, I will just erase them all because they will all change. So first we have the derivative of the active current in the DQ frame with respect to the phase of bus K. So it's minus V of K times BKK. B, by the way, is the imaginary part of the admittance matrix. Minus active power times the sine of the phase of bus K. Plus reactive times cosine. Everything should be all right. So the active one is V times G. G is the real part of the admittance matrix, minus reactive current times sine, minus active current times cosine. And now down here, this one is the derivative of these equations with respect to the phases of other buses, not the same bus. So first one, you can see that there is a kind of a mismatch in the nomenclature. Sorry for that, because here I'm using I, and here in the code there is this L. This L is doing the role of I in the slides. There are some other mismatches as well. Sorry for that. So B K L times cosine of phase of L minus phase of K plus GK and sine. Okay. I think everything is all right. This one. Yep. So now the derivatives with respect to the voltage. I should probably have said it more clearly before, but in this formulation, this polar formulation, the variables that we want to find are the voltage levels and the phases of the buses. And here we can just copy paste, because if you take a look, this derivative is identical to this part right here. So let's do that to save time. And the one below is identical to this part. Yeah, so if I have done everything correctly, now I have changed the calculation of currents following the DQ frame, and also updated the derivatives according to these new equations. And now we should get a proper estimation, hopefully. If I don't know if I messed anything up. Let's see. Apparently, yes. Let me try to see what's... Yeah, because if you take a look at this line of code, line 87, I'm establishing my mismatches based on this delta IR and delta II. This is another problem with nomenclature. This is active current and this is reactive current. But now I have this DQ, which my mismatch should be given according to this DQ. So it should be enough that I do this. And also here. Let's see. Hopefully it will work now. Yeah. So I don't know if it was clear, but the problem is that I was doing all of those calculations, but I was not actually using the calculations to update the iterative process in the Newton-Raphson algorithm. And now I'm doing that. So as you can see, the estimations were quite off before. And now you see that there is a very good mismatch in the currents. And the result usually is much better, actually, because here there is this piece, these lines here, they are representing the system, and I am completely neglecting the filter of the wind turbine, and also I'm approximating the impedance of the transformer of the wind turbine by 0.1 pu reactive. This is because the actual values are protected by intellectual property of Siemens Gamesa, and I cannot just show it here. So if we had the actual values, this would be pretty much a perfect match in these estimations. But the message here was that I just wanted to show uh, a few of the challenges that show up when we are trying to do this. And this is just one of so many, but just for you to get a feeling of how it is to go through this process of doing this estimation to power flow methodologies. So if we go back to the presentation, I think the last one that I showed was this one with the derivatives. And this is just to show some of the results that I am getting in my studies. It's very similar idea to those 3 cases that we just did in MATLAB, but here we have a bunch of cases. These are 72 cases. And with more variety of SCR, X by R ratio, and many other parameters. And also these areas here, I also forgot to mention that the 3 cases that we addressed just now in the codes that I shared, they are for 3-phase faults, which are the most simple ones in terms of modeling. So, but here we have this blue area with three-phase faults, the green area with phase-to-ground faults, and the red area with phase-to-phase faults, just to show that the approach can work for different types of faults. And yeah, this is for the voltage, this is for active current, and this is for reactive current. And you might be wondering why some cases we don't have this red plus. The pluses in general, which are the results from the proposed approach, is because we are on purpose simulating some cases that are problematic, because depending on the fault location, depending on the SCR and many other parameters, it's there is simply there is no equilibrium point. Basically, the turbine would become unstable if the fault is not cleared fast enough. And for these cases, also a steady state approach such as this one will not find an equilibrium point because there is none. And just to exemplify this first case, for example, which is one that we could not converge, this is the time domain result from the EMT simulation. So you can see that it is quite a mess. Although it is a three-phase fault, you see that there is a reactive injection in negative sequence, and things are going crazy. So yeah, no way that Newton-Raphson can converge. And that's pretty much it from my side about this SCC estimation. I don't know if there is anyone there from electrical engineering that might be interested on this, but feel free to reach me if you want to know more details. This is an ongoing work, and I am, but as I said in the beginning, I'm about to finish my PhD, and there will be work left, things that I will not have the time to address. So could even become some other projects, who knows? But that's it. Thank you very much.